Sorry about it. Yeah? All right.
I'll sit down so I don't trip on the way up. That'd be embarrassing.
Oh. All right, let's go ahead and get started, I guess, right? We're ready to go? Cool. Well, for those of you who are here, I guess you survived night one at the con. Congratulations. We just have a few announcements before we get started. There have been a few items that have been turned into lost and found, so if you're missing something or you no longer have your phone or something, go ahead and check in with registration, and if you can identify the item, you should be able to get it back. Also, for those of you who are not aware, we are selling bags of crap at registration, and they're just grab bags of prizes, and there's different sizes depending on how much you want to donate to a good cause. I also, before we get started, for those of you who sat close, I have a few giveaways. So if anybody wants a shirt from last year, then I also have a moose to give away. There's a lot of people.
Those are nice throws.
Thank you, thank you. All right, let's go ahead and get started with our first talk of this morning. It's on Cockroach analysis by David Dorsey. David.
So I imagine the title gives you how I feel about these files. So, like I said, I'm David Dorsey. I'm currently at Click Security in Austin. Been on the defensive side for a while now. Standard stuff I've been working on over the years. And I started to do data analysis and machine learning a couple years ago. So, why'd you guys wake up early to come see me? That's a good question. But what I'm here to talk about is how you can take a large amount of data and turn it into information you can act on. We're going to, it gives you starting places to hunt and find new, interesting, and hopefully unknown malicious files. It doesn't rely on easy to avoid signatures. And so it's essentially heuristics on, non-trivial boundaries in high-dimensional space. We're talking, in some cases, up towards 90 different attributes we're going to be looking at. So first we're going to talk about the tools I use to do this. That'll be quick. A little bit of vocabulary so everyone hopefully understands what I'm talking about. And then we're going to jump into the Java and Swift analysis. And I'll take you through the iterative process of exploring the data, extracting features, testing them out, and seeing how we do. And then we'll wrap it up, and then you guys can ask me questions. So first off, we used IPython to do our analysis. It's a great tool. It's interactive, browser-based. It's easy to share your results with others. I actually have 2 IPython notebooks that you can get to now to look at the data. You can see the methodology we used. IPython's a great way to show other people exactly the process you used. And I think that's important so other people can go, okay, I can see what you did. Here's where you did wrong, or here's where I think you could have done better. It's a good collaborative. Pretty much kind of like an awesome version of an array of dictionaries. It gives you a great way to slice and dice your data. Matplotlib, just an easy way to create graphs and plots. Most of the graphs you'll see in the presentation, I created these. The code's really easy to use. If you look at the notebooks, you'll see how easy it is. Scikit-learn, it's machine learning in Python. It makes things really easy. It unfortunately doesn't support data frames, but it's super easy to go from a data frame to something scikit-learn can use. So data science, it's everyone's favorite buzzword. So what really is it? Well, I think it's asking your data questions and then hopefully getting actionable information from it. To properly do this, you need someone with subject matter expertise, someone's really good in statistical analysis, someone to write the code to do all this. To find that in just one person is like finding a unicorn. Fortunately for me, scikit-learn pretty much took care of the coding and the math side of things, so I just had to provide the subject matter expertise. So I'm definitely not a unicorn. Ground truth, it's essentially the accuracy in your labels. Ideally, you want 100% accuracy. And it's not always easy to get, but because it can be time consuming. But if you have crap data going into your algorithm, you're going to have crap information coming out. Bias and variance. Bias is, is essentially the errors in the assumptions in your algorithm. Kind of like the example I'm showing on the dartboard, it's kind of like just always being off from the bullseye, assuming bullseye is your target. Variance is just kind of the sensitivity to your training set. In the dartboard example, if you have high variance, you're hitting all over the board. Low variance, you're hitting all in one spot. A high bias can lead to underfitting the data, where you don't match the data very well. And high variance can cause overfitting the data, where you try too hard to fit the data. And here's two quick examples of that. The one on the left is high bias. It's kind of an extreme example where it doesn't care about the data. It's just that red line, and you can see the data there. And then the high variance is the one on the right. You see it's trying really hard to fit every exact point on the graph, rather than trying to just get the nice smooth blue line where it's a good approximation of your data. So I'll be showing lots of box plots. It's a great way to display the distribution of your data. The middle line is the median point, and the box contains the 50% of your data, and then the whiskers there contains the other quarters on each side. Cross-validation. It's a technique for seeing how well your data will do on an independent set. You randomly partition the data, you train on one set, and then you test on the other, and then you repeat k times. In our notebooks, when we do cross-validation, we randomly select 80% of the data to train on, and then test on the other 20%. And we do this 10 times to make sure that we just didn't get a lucky training set. Decision trees. They're kind of a flowchart-like structure where each node represents a test you can do on your data, and then each branch is the outcome of that answer. The example here, I think, is one of the classic Titanic. If you survived the Titanic, and if you were male, no, then you have then you might have survived at a higher rate. And it's just, a flow chart, and it's fairly simple. Random forest is the algorithm we used. It's a randomly group of decision trees. We selected it because it's pretty good at controlling variance and not overfitting your data. And the classification answer we get from it is the label that appears most frequently. Since in each of my examples I only use 2 labels, 50% is our threshold, so if more than that, then that's your label. So the data, we have about 300,000 uncompressed Swift files and 370,000 Java class files. And this is where you can get your IPython notebooks. We have a data hacking repo on GitHub at Click, and it's where we put all of our various notebooks that we find interesting from different presentations. There's much more than just the 2 notebooks I'll talk about on there. You can get the data, play with it, and then contact us. If you think we could do something better, we'd love to know. And if you think we did something wrong, well, we also love to know that too. By no means do I think this is the end-all be-all, but it's just it's a good way to go about doing things. So Java. So I don't really want to get bogged down in the nitty-gritty of the format, but there's lots of information you can get from the file. I mean, simple things like version, class name, the constant pools, where amazingly it contains the constants in the file, strings, method names. Your access flags are the permissions and the properties of the class. And the methods, obviously, the actual code. So those 370,000 class files, they're probably all benign. I don't have labels for them. From where we got the data, I'm just assuming they're all benign, but it's quite possible that there's some malicious ones in there. And then I have 2,000 known malicious ones, and I verified that by uploading all of them to VirusTotal, and I think I made sure they had at least, I don't know, 10 detections. But it's a lot of data to start with. So we first start off with just grabbing 500 each. It's manageable, and you can get hopefully broad strokes about your data, and then you can apply to the larger set. So the first thing we did is look at the file size, and you can see they're usually fairly small. The malicious ones, maybe they're a little bit bigger, but if you look closer down at where most of the data is, you can actually see that, okay, the malicious ones on average are maybe a little bit bigger. So that's, that could be interesting, useful information. Next, we look at entropy. We're looking at the entropy over the entire file. Maybe we need a better idea would be to look at entropy in certain sections, but right now we just did it over the entire file. And you can see that, the malicious ones, a little bit higher entropy. Next, we looked at the number of items in the constant pool, and you can see that the malicious ones can have some really high amounts, but most of the data is crammed there at the bottom. So if we zoom in on that, you can see, okay, the malicious ones tend to have a little bit more. Next, we look at the number of methods. Maybe there's a lot of overlap here. Probably not a good way to distinguish between the two. Then we look at the number of interfaces. So they're pretty much almost always zero. Pretty much all the features you extract, they're not all winners. Some of them aren't better than others. So we take this information and a few others. We make our first pass classifier. We grab the data we just talked about. We grab them versions, the number of access flags set, that sort of thing, and then we throw it to random forest, and we run cross validation. And we got 92, about 92, 93%, with a fairly big margin of error. It's not bad. It's not great either by any stretch of the imagination. But we just used the data that we could really quickly get, and 93% isn't horrible for that. We can look at the data a little bit further, break down the numbers. Again, when we create this diagram here, we grab 80% of the data to train on, and then we test on the 20% of the data. And you can see here if the false negative and false positive rates are about the same. So we know that it works equally well on the labels. It's not really great at labeling benign files and fairly poor at malicious. They're about equal. So the next thing we want to know is, well, how important were those features? And so we can have the algorithm, so we can have random forest tell us which features were more important than the others. And you can see the entropy, the constant pool size, and the file size were the most important ones, and that kind of makes sense. We saw the box plots, and we saw the distribution of the data that way. And then the other ones, they start falling off as not as important. So like, okay, this makes sense. This is useful information for us. But clearly, we need more features, and there's still plenty more to get from the file. We have method names and attributes. We still have the class name, superclass name. But first, we'll look at the method names, because that could be interesting. And so we look at the benign ones. Yeah, these all look right. Okay, they look normal. And then you look at the malicious ones, and some look okay, and some look like my 2-year-old son was in front of the keyboard and typed them out. And so so clearly those look bad, but random forest requires you to have a number inputted into the algorithm, so we can't exactly input text to it. So how do we extract, what features do we extract from that text that we can convert into numbers? To do that, we took some inspiration from a spam filter. Some of the features the spam filter we looked at had was the length of consecutive lowercase letters and uppercase letters and digits. So it was like, okay, let's try that. And we took the max length from all the method names and then the average length of all the sequences of those. And we wanted to explore those. So we look at the lowercase letters. If it's really high, it's probably more malicious, but there's a lot of overlap. Same thing with average length of lowercase letters. If you look at uppercase, same thing. Average length again, same thing. It's a little disappointing. Digits, it's almost always 0. both average and stuff. And so we use that information, we throw it our cross-validation again. We have a slight improvement, it's still in the margin of error. So, maybe this was good, maybe this was bad, or not as good, maybe not necessarily bad. But it wasn't as hopeful, it wasn't as good as I hoped it would be. And then if we break down the numbers again, again, you can see that it works equally well on both the malicious and benign. It doesn't favor one label over the other. If we check out the importance again, still the first three are the same as the last time, and that's no surprise because we didn't see a lot of separation with the method names. But, so clearly we need more features, and we still have, still plenty of more features. So next up we're going to look at the class name. So we first start off with the benign class names. Look at them, okay, they look okay, normal words, maybe they're pretty long, there's lots of slashes. Okay, that's about what we can, look at it. And then if we look at the malicious ones, like, okay, my son was typing these out again, and, they're fairly short, not many slashes. Okay, so maybe we have some good features there. And so that's the features we extract, the length, number of slashes, and then we do the spam filter features again. And so we look at that. So when we look at the class name, some fairly good separation. The malicious one's much shorter. Look at the slash, malicious ones, almost no slashes, some one, and the good ones, the benign ones, usually have slashes. So there's some good separation there. Then we look at the lowercase letters. Okay, now we're starting to get some separation there, so that's good. That's encouraging. Same thing with the average run. So we do our cross-validation again. Hey, it looks like it might actually be useful. We got 99.4%. So let's break down the numbers. We run it, the confusion matrix on again, and okay, it told us we were perfect. Now, if you believe that, well, can I go work for you? So there's some things we still want to play with here. So there's knobs you can turn with random forest. Like I said before, by default, it's whatever label was over 50% is what it's called, what we labeled the data. But you can change that. So you can increase the threshold to decrease the false positive rate. It comes at a price of lower detection, of course, but if you're worried about false positives, you can handle that. You can also decrease the threshold to increase the true positive rate. So maybe if you just want to definitely filter out the good ones, and be okay with some benign ones passing through for further inspection later on, you can decrease it. So we wanted to play with the data a little bit, and so we set the threshold to 80%. So 80% of the trees had to say this file was malicious for us to call it malicious. And we did that, and we still had actually surprisingly good results. We only misidentified 3 of them. So that was encouraging. So then we wanted to flip that. Let's set it down to 20%. So only 20% of the trees had to say, yes, this file is malicious. And we actually only misclassified 1 of the benign files. So that was also encouraging. So what that means is our algorithm was actually fairly confident of its label. Here's the distribution of all the scores from that. And you can see that, yes, they're either way on the left or way on the right. So the algorithm's very sure. So now we want to check out the feature importance again. And you can see, I think I have 8 there, and 6 of them are, it might be 9, are almost all of them are based off of the class name. So this is, good and bad. It's good because, we seem to get good results from it. It's bad in the sense that we might be overly reliant on one particular feature. So if an attacker, happens to change their behavior on that particular field, our great classifier now turns into a very useless one. But that's a future problem. So how does it work on the 366,000 files that we have? So it ran it, 340,000 of them were marked as clean, which I said is less than 50% of the trees marked it as malicious. 11,000 were in this, what I call a gray area, where 50 to 80% of the trees marked it as malicious. And then 15,000 were malicious, which is 80% of the trees or more. And that's fairly horrible. I mean, I totally don't think 15,000 of these files were malicious. It was kind of disappointing, but really it's Iago. It's not really that big a surprise. We started with only 500 of each. That's really not enough data. So let's use more data. So we created a new classifier. We had 2,000 maliciously labeled ones, so we used all 2,000 of that. And then we took 2,000 of the files we were testing on, randomly selected 2,000 of those, and marked them as benign. And then we ran cross-validation on it, and we got a 99% again. You know, so that much like before, or the 500 file classifier, but now with much more data. Check out the confusion matrix. Again, it looks good, you know, equally good on benign and malicious. And then we run it on the rest of the files. Now, the first time through, you know, this result was actually a little surprising to me. The malicious ones went way down. Now we're less than 1,000. So that's almost down to a reasonable number, you know, over the course, you know, collecting files over the course of a year and a half. But you have that 64,000 in the gray area. That was surprisingly large. I'm not sure why it was so high yet, but you know, it was high. But since I didn't quite like the results, I want to say, okay, maybe it was just a poor training set. And so I took another random 2,000 files and tried it again. This one I got a much better result. So only a little bit over 3,000 files were in the gray area, and then a little bit over 1,000 in the malicious area. And they're still high, and so clearly I think the classifier needs more work, but I was much happier with this result than the one with the 60,000 gray. And then I ran it again, another random 2,000 files, and got similar results to the second run. So you can see that first run with the 60-some-odd thousand gray areas, there was something interesting in that training set. Maybe it was a poor set, and but you know, this is just stuff this is just information you can get from your data that you can, you know, when you play with it. So to sum up the Java section, you know, we can detect malicious files using data science. Clearly that we still need to do more work, but you know, we just started on this recently, and you know, we're getting fairly good results, I think. There's variability in my data, obviously, but we have it, so we can train on more of it. We need more data, and we end up with a classifier that's fairly good at classifying class names. So next up, you know, more malicious files, better labeled data. You know, I just assumed those 2,000 files were benign. I should probably verify that. You know, we start just simple labels, good, you know, good, bad, but we can probably get, you know, more sophisticated labels like the exploit kit or the CV number that it uses, and then, you know, hopefully, you know, extract features that can maybe label that too. Then we still need to extract, you know, more features from the file itself, more information about the method and class names, more features about the methods, maybe, you know, an actual look at the bytecode, maybe an n-gram analysis of it. There's lots of stuff we could do still, and that's just, you know, it's coming up next. You know, it's what we have to do next. So now we'll switch gears and go over to Flash. So I have, you know, a little under 300,000 Swift files. They were all uncompressed. If I had them compressed, I uncompressed them and got rid of them. Got rid of the compressed version. I only had 628 malicious files. That was smaller than I wanted, but I was limited by what I could find. So, like before, I start with 500 of the benign ones, and I just grabbed all the malicious ones because, you know, I was normally going to do 500 of it, but, you know, what's the difference between 500 and a little over 600? Again, I used VirusTotal to verify that the malicious ones were malicious and that the benign ones were benign. So the Swift file highlights, you know, you have the in the header you have the version, the information about the size of the SWF on the screen, the frame size, the rate, number of frames in it. And then, there's tons of tags in the, that's how, SWFs are divvied up. Everything's in a specific tag. And so there's, any number of tags, and it's supposed to end with an end tag. So we looked at that, and so we wanted to see what versions were we seeing, and then were they malicious or benign. And, most of the malicious ones seem to be version 9. That's not terribly surprising to me because that's when ActionScript 3 was introduced into SWFs. And that's kind of like your JavaScript for SWFs, and so it made it easier for attackers. But, it's overall, it's a lot, there's a lot of equal amounts. I mean, as in, for like 10, it seems to be about equal on benign and malicious files. So not a lot I think we can really read into that from this. We look at the file size again. There's a lot of overlap here. So I didn't think this was, a good separator. Entropy, actually this was a little surprising that the malicious ones had less entropy. I'm used to thinking that the more entropy something has, it's bad, but that wasn't the case in this one, so that was interesting to me. Frame count, see that most of them were, the benign ones were really low. I mean, you don't even see a box. That's how many were really low. And as it turns out, almost all of them just had a frame count of 1. And then frame rate. A lot of overlap. It doesn't look like a good separation of data here. Same thing with the area of the frame. It's a lot of overlap. Again, with the perimeter, a lot of overlap. Maybe the small perimeters are more associated with malicious, but it's, I got this and I was like, this is going to be my first pass classifier. I'm thinking it's going to be horrible. But I did a cross-validation and it was 96%. It was surprisingly good. Probably artificially good. But I was quite surprised by that because I didn't think I had good information there. But the algorithm tells me it did, so I'm going to trust it over myself. So we break the numbers down again. It's about the same as the Java classifier. It's pretty good at labeling benign and malicious both equally well. Check out the feature importance. Entropy was the highest, and that makes sense because looking at the box plots, that was probably the best separator. So, I think we could do better, so we tried. So we have all that tag information. A tag can exist multiple times in the file, but we only take into consideration that it does exist. So if it exists 10 times or 1 time, we don't care. We just say it exists in the file. And then an end tag should be the last tag. So check that out. So the number of tags. So this might be good. So you can see the malicious ones, they typically have a small number of tags in the file. And the benign ones, there's a very big spread, and some can be extremely large. So then we break down and let's look at individual tags, see if any of them seem to favor one label over the other. Place object 2, just one of the tags that jumped out at us. If it does have one, it's probably benign, but there's a few with malicious, so that's some interesting information. Do ABC, that's the tag for ActionScript. It's not surprising that a lot of the malicious ones have it, but a lot of benign ones have it too, so it's not that great. Then there's the do ABC define. That's apparently the deprecated way to do ActionScript. I think there's 1 or 2 benign ones that had it, and only a few malicious ones. But if you do have the tag, it definitely looks like you would be malicious versus benign. Again, just another tag that if we saw that. If you had this tag, you were likely benign, but most of them don't have the tag. So this is where the high dimensional space and the weird decision boundaries come into effect because there's a lot of different variability in all these. And then the end tag. So every file, I think, according to the spec, is required to have one, but apparently it's much more forgiving than that. So most of the, almost all of them had end tags, but if you didn't, you're more likely to be malicious, though even some of the benign ones just didn't have an end tag. So we took all this information, so we had the number of tags, and I think there's some 80-odd tag distance that we threw in there, and we did cross-validation, and we got pretty much the same results as before. It was fairly disappointing, but it's just the way it goes sometimes. Sometimes you think you have a great idea, and you add it in, you do the work, and see the results, and you're like, oh, that makes me sad. Breaking down the numbers again, like before, it's equally well labeling each class. Maybe there was a slight improvement, but it's within the margin of errors. It was fairly disappointing. Look at the feature importance again. Well, the number of tags, that jumped up. It showed up relatively high on it, but not enough to really make a difference in our overall results. So then, based on experience, I know that ActionScript, is used a lot for malicious, in malicious files. So I wanted to say, okay, maybe there's some features there we can get that might help us, identify malicious ones. So ActionScript, brief overview, it allows Flash to be interactive. There's multiple versions. I think they're on the 3rd version right now. The ActionScript itself is structured similarly to a Java class file in the sense that there's a constant pool section for methods and attributes. And I really, really, really hate the ActionScript file format. There's variable length fields so you have to do a bunch of bit manipulation. I don't know why it exists. I hate it. So anyways, the data. So we looked at the number of strings that are in the ActionScript. It's disappointing, a lot of overlap. If you have a lot of strings, you're much more likely to be benign, but there was a lot of overlap. So it was like, not much there, maybe. I mean, at least looking at it this way, I don't have a lot of hope. Then we looked at the mean to median string length ratio. So you take the average length of all the strings and the median length of all the strings and divide that. And typically a higher ratio there means it's more suspicious. And that's because, in these cases, you have a bunch of short strings, and then you have a very long string that's the shell code, and then that long string throws off the average length, but it doesn't really affect the median length that much. So we want to look at that. And so we do have some decent separation there. You notice that the benign ones are really close to 0 there. That's because all the files that had no ActionScript get a value of 0 assigned to them there. So they're kind of anchored down a little bit just because of that. So we did the cross-validation on those. And maybe a tiny bit of improvement, but still not near as much as I would have liked. 97%. I mean, we're not talking bad, but I had hoped at least that we were going to do much better. Breaking down the numbers again, I think this was a particularly good training set. That's why it's above the 97%. But again, it's equally well about labeling benign and malicious. We check out the feature importance. We see the string count there at in the top ones, but none of the other ActionScript ones, were particularly useful or high in importance. So let's test it on those 290,000 files. So we did that, and 8,000 were in that gray area, and 2,000 were marked as malicious. That was way better than I thought it was going to be, honestly. Judging by our cross-validation result, I thought this was way better than the Java one on the first try. And again, we only used a small set of files. So maybe we'll get better results with training on more data. So this time I chose 5,000 files from the large corpus and set them as benign. And I ran cross-validation again. This time 99%, in a very small margin of error. So I was like, wow, that's much better. I'm actually now hopeful. Breaking down the numbers, it looks good, equally well on both benign and malicious. Check out the feature importance. Much like the smaller classifier, it's same feature importance. So now let's run it again. Now we're fairly decent results, I think. And maybe even manageable results. So 400 plus files marked as malicious, a little under 700 in the gray area. Considering we, gathered these files over the course of over a year, assuming an equal distribution of the files per day, it's almost a manageable number for an analyst to look at. That's not bad. So then we had the idea of, all right, we have all this information on ActionScript that we added to our classifier. What if, and it shouldn't mean anything to any of the files that don't have ActionScript, so let's limit our file set to just the ones with ActionScript. We run cross-validation again, and it's 99%. Well, it's just like the classifier that didn't care that we had non-ActionScript files in it. So like, okay, well maybe let's check it out in a large corpus. That usually gives us some good information. We had 153,000 of those. Most were marked as benign, only a small set for gray and malicious. But percentage-wise, it really didn't bias anything. It's the same amount, the same percentage of each section or each label was kind of as the non-specific classifier. So that was surprising to me, honestly. I thought that, if we focused one on just a classifier for Swift files with ActionScript, that would be better than the one classifier to rule them all, but it clearly was not the case. So in summary, we can detect malicious files using data science. This classifier isn't overly dependent on any one feature, which is kind of nice because in the Java one, if they change just one feature, they'd probably defeat it. This one, they would have to change their behavior much more. Creating separate classifiers for specific sets of Swift files didn't help us at all, and the classifier performed fairly well on the random set of files. I was happy about that. So next up, of course, more malicious files. That 600 really doesn't cut it. I need more. Like the Java, better labeled data, not just good, bad, exploit kits, CVE, anything else you could think of as a possible label could be good. I still think we can extract more ActionScript features, maybe some, n-gram analysis again, or a G-test analysis on the methods called. There's lots more information we can extract and play with, and hopefully, increase our results. So our highlights from today. So we can use data science to detect new malicious files. That's great. And it's without signatures, so it's not just, we're not just changing one simple string or a set of bytes to avoid it. It's much harder. They're going to have to change their behavior, which is harder to do than just changing a simple line of, line or a sequence of bytes. The Java classifier is heavily dependent on one feature. Again, that's good and bad. It's good because, it worked really well. It's bad because once they change that, it's going to not work really well. The Swift one, it was good on, it was not dependent on one particular feature or highly dependent. And so that way, to avoid that one, you're going to have to change a lot more things. And we see the more data we trained with, the better the results were. At some point, I'm assuming there's a diminishing returns, but I don't think I'm there yet. So we're really seeing this is a fairly useful method of talking with your data. Not to say that this is ready to go and you can just do all this and put it out in production. You're going to have to figure out how to productionize it and enable it to your analysts to use. But it's stuff you can do. It's relatively easy to do. The IPython notebooks can walk you through a lot of the steps we took, and You know, we're sharing it, so there's no harm in, you know, playing copy and pasting. We know we borrow from ourselves. Some things you want to try to avoid. I don't like, you know, being over-reliant on that one feature. You know, I think that especially in the Java case, that there's more features to look at that I think will be hopefully just as useful. So that way we're not overly reliant. And the other thing I think, you know, it's hard to avoid is sometimes you think you have this great feature and you really want it to work well, and then it doesn't. And then you're like banging your head against it, trying to get it to work, or maybe it's this, maybe it's that, and then you're just wasting a lot of time. Just, you know, pretty much trust your data. If it's telling you it's not good, even though you really love it, just move on. It's not always easy, and, you know, it can be frustrating, but, you know, otherwise you're just wasting even more time. And then test on a lot of data. You know, if we had stopped on the Java class files without testing on that large corpus, you would have thought it was great. But then when we ran it on the large corpus, you saw that it wasn't near as good as we thought it was. So where do we go from here? Well, obviously we need more data. Verify our data is labeled appropriately. More sophisticated labels, like I was mentioning, the exploit kit, you know, where if it came from, or the CVEs. And then extract more features. It's, you know, there's a lot more data we can get from the file, so we should get it and see how it works. And like I said, you can play at home. You can go to this site, our GitHub repo, to get the notebooks, and there's a lot of other notebooks too if you want. The information from the 300,000 files was relatively large. I didn't think GitHub would really like me uploading, you know, 200 megabit files. So if you really want that data, I'm happy to share it with you, but you'll have to contact me to get it. You can contact me on Twitter. There's my email address. And all the links you probably can't really read. If you look at the slides later, they're just links to a lot of the references I used. So on that note, any questions? We'll go up close first.
Are you going to post these slides somewhere?
Sure. I think the conference will, but if not, I'll post them and I'll send out a link to where they are at.
Have you considered any other classification algorithms, like unsupervised learning or even SVM?
Yeah, so I think actually in which one? I want to say the Java class. In the notebook itself, I also used, it was like the extra trees random forest. So it's like random forest, but even more random. And then I used an SVM as well, and I got similar lists. I didn't run them on the entire corpus, but it was just something to play with. And that's probably one of the things I should have mentioned. I used random forest because I'm most familiar with it, but by no means do I think that's definitely the right one to use. I'm all about using whatever one works the best.
I'm just curious if there's, you talked about being overly reliant on one feature. Are there any sort of good definitions for kind of how reliant you should or shouldn't be on just a certain number of features?
I don't think there's like a good definition, but the numbers next to the features that are used and gave you the weight the algorithm used, and I think I want to say the ones from the class name were up to over 80%, and just intuitively that just seems high to me. I mean, it's just intuition at that point.
You said you had a high degree of variability in the new classification on Java files. Did you ever explore using maybe like an ensemble or classifiers to limit your variance?
Yeah, so, you know, random forest is an ensemble one, but I think it's just the fact that I had so much variance was, I think, just my training set, and I just randomly selected, I think, a bad 2000 for the benign. But since I have the files, I really think I probably should have done like maybe 10,000 files to train on, or maybe even 50,000, and that would still leave me a lot to test on. and I think just more data will help control the variance there. Actually, I wasn't looking over here. I think that is it then. Thank you.